Welcome to the Explainer. Today, we are diving deep into a really powerful feature of modern C++ that makes your code so much faster: move semantics. It's all about a fundamental shift from making expensive duplicates to, well, just efficiently stealing the data you need. Now, at first glance, these two lines of code look pretty much the same, right? But believe me, their impact on your program's performance can be absolutely massive. One of these lines creates an expensive, slow duplicate of everything. The other, it performs a super cheap and efficient transfer. So let's dive in and see how this works.
Okay, here's how we're going to break it all down. First, we'll look at the problem itself, the cost of a copy. Then, we'll get into the secret handshake of C++ that makes all this possible: lvalues versus rvalues. After that, we'll learn the art of the steal. And finally, we'll see how to put it all into motion and wrap up with the key takeaways.
So, what is the big deal we're trying to solve here? Well, it all boils down to the high price of making copies. For simple things like an integer, who cares? It's trivial. But for big, chunky objects that manage a lot of resources, think a string holding a giant block of text, or a vector with thousands of items, copying is an absolute performance killer.
Think about it this way. Copying an object that holds a huge file or a massive list of customers means you have to allocate all new memory and then painstakingly replicate every single piece of that data. It's slow, it's resource-intensive, and a lot of the time it's totally unnecessary, especially if the original object you're copying from is just about to be thrown away anyway.
To really get the solution here, we first need to understand a fundamental distinction the C++ compiler makes. It's all about the difference between something called an L-value and an R-value. This distinction is really the foundation for how all of this magic works.
First up, we've got L-values. The easiest way to think about these is that they're things with a stable home in memory. Like a variable you've declared. So if you write int x equals 5, your variable x is the L-value. It has a name, x, and it has a persistent address you can keep referring to.
And on the other hand, you have R-values. These are the temporary, fleeting values, the transients of the C++ world. In a line like int z equals x plus 1, the result of that expression, x plus 1, is an R value. It just exists for a moment, long enough to be assigned to z, and then poof, it's gone. It doesn't have a name or a lasting address.
And this is the aha moment. This is the whole key. Since these R values are temporary and they're just going to be destroyed in a microsecond anyway, we don't need to waste time carefully making a copy of their contents. We can just plunder them. We can steal their resources and leave the empty husks behind. This is the core idea that makes move semantics possible.
So how do we actually perform this steal in a way that's safe and structured? Well, C++11 gave us the perfect tool for the job: the move constructor, and its partner in crime, the move assignment operator.
Now, the key to this whole mechanism is this funny-looking syntax right here, the double ampersand. And no, that's not a typo. It declares something called an R-value reference. It's basically a special signal to the compiler that says, hey, this version of the function is specifically designed to catch those temporary R values we were just talking about. It's the gateway for our stealing logic.
So let's break down what happens inside. It's really just a simple two-step heist. Step 1, steal the goods. Our new object's data pointer just grabs the memory address from the temporary other object. That's it. No deep copy, no new memory allocation, just a lightning-fast pointer swap.
Step 2 is just as important, though. This is all about cleaning up the crime scene. We have to set the temporary object's pointer to null pointer. And this is absolutely vital, because it stops the temporary object's destructor, which is about to be called, from deleting the very memory that we've just stolen and now rightfully own.
And this diagram just illustrates the whole process perfectly. Before the move, object A owns the data hello. Then, the move operation gets triggered. Object C doesn't copy the data, it just yanks the pointer right out of A. And after the operation, C points to hello, and A is left in a valid but totally empty state. It's a beautiful transfer of ownership, not a clunky duplication of resources.
Okay, so we've got the mechanism, but how do we tell the compiler when to use it? Especially with L-values, those objects with names that we know we're finished with but aren't technically temporary, how do we signal that it's okay to move from them? Well, this is where this standard library function, stdmove, comes into play. Now, I gotta warn you, its name is a little misleading. It doesn't actually move anything by itself. It's really just a cast. It's our way of giving the compiler a permission slip. We're saying, hey, I know this object here is an L value, but trust me, I'm done with it.
you have my permission to treat it like a temporary rvalue and go ahead and steal its guts.
But, and this is my favorite part, in many common situations, you don't even need to write std_move. The compiler is smart enough to figure it out for you. Just take this super common example, creating a temporary object right inside a function call, like when you push myStringWorld into a vector. In this case, the compiler sees that myStringWorld is a temporary rvalue, and it automatically calls the move constructor, not the copy constructor. So the number of expensive, deep copies that are made is exactly 0. This is a massive automatic performance win when you're using standard library containers, and it's a huge reason why modern C++ is just so much more efficient out of the box.
All right, we have covered a ton of ground here, from the theory of lvalues and rvalues to the practical application of move constructors. So let's just boil this all down and summarize the most important points that you need to remember when you're writing your own code.
Here are the rules of the road. First, use std_move when you want to explicitly say it's okay to move from this object. Second, if you're writing a class that manages resources like memory or a file handle, you should absolutely give it a move constructor and a move assignment operator. Third, mark them no except. This gives containers like Vector even more opportunities to optimize. And last but not least, always remember to leave the object you move from in a valid, predictable, but empty state. So, the next time you're digging through some C++ code, I'll just leave you with this question to think about. Look for those places where you're creating temporary objects, or maybe passing big objects around by value. Understanding move semantics isn't just some academic exercise. It's a real, practical tool for writing faster, leaner, more efficient code. Thanks for joining this explainer.